Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are three experts in quantum Monte Carlo: Gustavo Ordoñez of Moody's Analytics, Giorgios Korpas of HSBC, and Iordanis Kerenidis of QCWare. We talk about what quantum Monte Carlo is, the difference between classical and quantum Monte Carlo, how soon before it becomes a production-ready algorithm, and much more. We hope you enjoy this episode.
Hello, Gustavo. Hello, Iordanis. Hello, Giorgos. Thanks for joining me today.
Hello.
Hello.
So, Gustavo, let's start with you. Who are you and what do you do?
Right. So Gustavo Ordoñez. I work for Moody's Analytics. I'm a senior director, data scientist, and I basically work in research. So I build new models, explore new ways of using the data to create new ways of looking at what can be done and how we can actually make better decisions faster, more accurately. That then power our products. So that's what I said. And part of what I do is to help the quantum ecosystem within Moody's Analytics that is led by Sergio Gago, that I know has been in the podcast in the past. So I support Sergio in that journey of establishing a quantum computing group at Moody's Analytics. And the reason for that is that I am a passionate, I'm very, very passionate about quantum computing. And I was a research physicist in the past, many years ago. And that is where I discovered quantum computing. And, I've been keeping an eye on it as a hobby for many years. And then the last 3 or 4 years, I've been actually looking at it on more serious, on a more serious note, because it's becoming more and more likely that it's actually going to have an impact on the industry in the medium term, I would say.
Excellent.
So that's me.
And Gustavo, what city are you calling from today?
Well, I'm calling from Scotland, actually, Stirling in Scotland. So it's a small city, a bit in between Glasgow and Edinburgh. But I'm based in our offices of the Moody's Analytics offices in Scotland and in Edinburgh. But I'm actually now working from home today, and I'm here in Stirling.
Excellent. And Iordanis, I think you're calling from Paris. Who are you and what do you do?
Hi, Yuval. Yes, I am calling from Paris. My name is Iordanis Kerenidis. I'm the head of quantum algorithms for QCWare, which is a quantum software company. Before that, I started working on quantum algorithms more than 20 years ago. I did my PhD in Berkeley, and then I was at MIT. And for the last 15 years, I'm based in Paris. I was working with CNRS at the university. And for the last 3 years, I'm working for QCWare, where I'm working on optimization and machine learning for the finance domain, but also other domains. And yeah, we have worked quite a bit with different financial institutes, in particular on the Monte Carlo methods. So I'm very happy to be here.
I'm glad you're here. And Giorgos, where are you calling from and who are you and what do you do?
HSBC. I have a slightly different background than most people involved in quantum computing, since I come from very theoretical aspects of physics. I have a background in string theory and topological quantum field theories. And within HSBC, I co-lead the programs in quantum optimization, quantum Monte Carlo, aspects of classical machine learning as well. And just like Gustavo and Iordanis, I'm extremely passionate about the topic, and I'm very happy to be here.
Excellent. And I'm not an expert on quantum Monte Carlo, certainly not to the level that you are. And maybe, Iordanis, you can tell me what Monte Carlo is And Gustavo, maybe you can tell what the difference between Monte Carlo and Quantum Monte Carlo. So, Iordanis, why don't you go first, please?
Hmm. Sure. So I'll try to be, to say it in a simple way. As I understand it, I'm also not a finance expert, but the idea is that we have some assets that we want to price, for example, and we want to understand how to price them. And the way we do it is by constructing some sort of model for the market, for example, which mathematically is some stochastic process. And what we do is we try to run many different scenarios, according to this process. And for each one of these scenarios, we compute the right price for our asset. And then once we do it many, many times, we aggregate all of these results and we compute on expectation what we say is the correct way to price this asset. So this is kind of the Monte Carlo way of pricing some asset. And Gustavo can continue on the quantum, I guess, way of doing it.
Okay, so yeah, thanks, Iordanis. So the idea behind Monte Carlo is actually very simple. You basically you have a problem that is too difficult to solve analytically, so you can only tackle it numerically. And what you do is to draw from a random distribution that you can draw efficiently from, and basically, the draws from that random distribution that end up in the solution space that you're interested in, you keep, and the rest you discard. And by doing that, you can infer the actual answer to the problem that you're looking for. That is in essence what the Monte Carlo technique is, and it's extremely flexible. It works for a very, very large number of problems. It's also very powerful in the sense that it can solve very high dimensional problems efficiently. But at the same time, what I say efficiently actually is in the sense that it's very easy to code, very easy to get to run, etc. But it's actually not very efficient in the sense that it actually takes a long time to run, because you have to draw many samples from this random distribution. What Quantum Monte Carlo does is to leverage very well-known or a very well-known set of algorithms in the quantum algorithm domain, namely the Grover algorithm, the amplitude estimation algorithms, to do the same that you would do classically, but quadratically faster. So that means if the particular problem you want to solve classically takes, say, 1 million simulations to reach the level of accuracy you are interested in, in principle, theoretically, on a quantum computer, you could do that with only 1,000 samplings, which is a huge gain. If you take into account, that many of these problems are huge problems for which you need very large computer clusters in the cloud to run overnight to be able to actually get to the answer. So that is why this is one of the key problems in quantum finance that have been explored by financial institutions. And but as I said, it does in essence, does the same thing. Is this sampling from a distribution? In this case, because the quantum circuit runs on a machine that is already stochastic by nature, what you do is to leverage these well-known algorithms that I mentioned to actually do the same quadratically faster.
So, Yorgos, in your opinion, what makes quantum Monte Carlo, at least theoretically, better than regular Monte Carlo? Is it that the random distribution for quantum could be real? Is it the ability to run multiple scenarios simultaneously on a quantum machine? Why the big interest in quantum?
I would say that it's essentially what Gustavo mentioned, which is that it's a sample complexity. So normally, like if you have a very simple case where you want to run a classical Monte Carlo with say 100 samples, your confidence interval for this estimation would scale proportionally to the 1/square root of 100. So that's an error of 0.1. But essentially, quantumly, using these algorithms that Gustavo mentioned and Iordan has been developing for a long time now, you can do this you can compute this confidence interval in a scaling that goes 1/m. So where m are your steps. So for 100 steps, that would be 0.01%. 0.01. So that's 1%. So it's essentially this improvement in accuracy that you obtain, or which can also be converted to speed. However, I would like to know there are several limitations as to that we maybe discuss at, at certain point. Yeah.
Iordanis, I think you work with customers on a variety of fields, maybe not just finance. Is Quantum Monte Carlo applicable to additional areas, or is it primarily used in the finance field?
Mhm. I mean, it it is a very basic mathematical way of trying to calculate something. So it does have applications in many other domains. But I think the finance one is one where it's really used all the time and very much. And this is really where we're trying to see exactly how quantum can help or when quantum will help. Because as Yorgos was saying, there are some caveats in this algorithm. The first one is that in order to get the speed up from 1,000,000 samples to 1,000 samples, which is amazing if we manage to do it, right? We need to have these quantum circuits, which are very deep, like let's call it 1,000 times deep. And this necessitates very good quality qubits, which are not the qubits that we have today, but we hope, to get at some point. One of the things, one of the way to kind of maybe try to overcome this obstacle is also based on some work that we did with Coleman Sachs that says a very simple thing, which is that if you want to get this 1,000 times faster algorithm, then you need this very deep 1,000 deep circuit, but you can get a 10 times speed up if you have a 10 deep circuit. So you don't have to wait until you have these very, very good quality qubits to get the entire speed up. You can start getting smaller speed ups, which hopefully will still be relevant, right, from a business and finance point of view, with much simpler quantum circuits. So this is one of the two reasons why we now think that Quantum Monte Carlo may not be so far ahead in the future, but a little bit closer, let's say midterm. And the second quick comment I want to make that, as we said, up to now, what we were counting is how many samples do we need to take from this process, from this distribution, right? One part that we don't talk so much in the quantum case is how difficult it is to actually take one sample from this distribution, right? Because in order to run this quantum algorithm, we actually need to do this sampling in a superposition in a quantum way in order to fit it into the quantum algorithm. And this is not obvious how to do, like some things like a Brownian motion or geometric Brownian motion very efficiently in the quantum case. And this is also a very interesting part on how do we make this part also most efficient. So then we may be able to not do only 10 samples, but 100 samples in order to get 100 times speed up. So putting these two things together, doing the stochastic modeling very fast and saving all the number of samples that we need can actually, we think, provide an end-to-end solution, quantum solution to the Monte Carlo pricing problem in the near future.
So, Gustavo, I'm curious about your perspective about how practical it is today. I mean, obviously, there are algorithms like Shor's algorithm that promise amazing things but are impractical using today's computer. Um, you work at Moody's. Are you using Quantum Monte Carlo in a production way today? Or if not, how far do you think they are?
Um, no, we're not using it, and I don't think we're going to be using it anytime soon. That's why in my opening, I mentioned maybe the medium term. A medium term, I'm talking probably 5 years, maybe 10 years, something like that. Um, I mean, the limitation right now is the hardware, as Iordanis was alluding to. We don't have hardware with enough fidelity to be able to really run these algorithms in a naive way. So we need to find ways to extract as much as we can with the noisy hardware that we're going to have for now, for the foreseeable future. Um, and therefore, uh, algo developers, what they need to do is basically find ways to play or find ways to deal with the fact that we're going to have noisy hardware. We're going to be losing some of the advantage that is promised by the theoretical advantage promised by the algorithm, the theoretical algorithms that we know today. But so to find ways around those limitations and still extract as much of advantage as you can. But I don't think that, as I said, I don't think it's going to happen anytime soon. However, another thing that I would say is that um, no one runs these in the classical term. When we run classical Monte Carlos, we never use the more naive way of doing this, or very rarely we do the more naive way of running these algorithms. There are many improvements that you can do on the classical side, like importance sampling or and other variance reduction techniques. There are many of them that actually give you a huge advantage already on the classical on the classical naive Monte Carlo algorithms.
So, Yorgos, maybe you want to add to that, and Iordanis, after that, you mentioned some of the work you did with Goldman Sachs. Maybe you could give us sort of a lay of the land of the improvements that you've seen in recent years.
But maybe some understanding first for the people who may not be so much aware of what we mean as quantum alternatives from Monte Carlo, and that essentially it's not one algorithm. It's essentially an amalgam of three, four, maybe quantum subroutines, quantum algorithms. And while indeed it's the case that if you want to run the original ideas, that's where they were developed in the 2000s, it's very difficult, as Iordanis has mentioned. He also knows very well, he's one of the co-developers of improvements of these algorithms, wherein, for example, you can take some of these subroutines and replace them with something else. This something else could be some classical part, for example. So there's some classical post-processing in the way as your algorithm develops, you can do some classical post-processing that may not be the best thing you can do, but it can definitely bring it to this time frame that Gustavo mentioned, the 5-year time frame. There are other there are other variations that Iordanis is much better to explain. For example, his coprime quantum altitude estimation, which is also very promising. So I think that it's not all negative by any means, but at the same time, I totally agree with Gustavo in the fact that there is some pressure, especially when you don't work in a university, to focus only on the algorithmic side. But quantum computing is three steps: it's data loading, it's compute, and it is readout. And maybe the community should also pay more attention to, for example, the problem that Iordanis briefly mentioned, which is the data loading, to do it more efficiently, in order to speed up in your computations and not bury your quadratic advantage in these overhead costs. And the same, of course, goes into having accurate readouts. So when we develop these algorithms that are so fundamental and they will be of such importance for financial applications, we need to take a step back and look at the bigger picture as well, because improvements in these sides, in the beginning and the end of the algorithm, actually can imply that the algorithm can come closer in the time frame for actual application.
Yeah, I totally agree with Yorgos that if we really want to see any of these advantages in practice, then we really need to take care of every single part of the workflow. And he was mentioning the data loading part of, again, how do we load these Brownian paths or things like that. And we have been working lately on this. It's not an easy thing to do, but we do think that we can provide very shallow circuits, like logarithmic side circuits, for doing this data loading part, which in turn would mean that the entire depth of the circuit and the quality of the qubits can now be much, much less. So, yeah, I would still agree that we are a 5 year out, to see quantum Monte Carlo starting to really bring something. I wouldn't put it closer than that. And to make it happen in 5 years, we do need the hardware to continue to develop and to advance, as the roadmaps are saying. So we believe that they will continue to advance the way they are thinking they can. And on the algorithmic side, as Yorgos was mentioning, we do need to keep working on it. So I don't want we shouldn't think of quantum applications as something where the algorithms are already there and we're just waiting for the hardware, right? We really need to push the algorithms as much as we can, because as Gustavo was saying, we do have to do with very noisy and not very big quantum machines, and we have to make the best out of them. And we really need to understand everything about them if we can actually, make a good use of them and really bring some sort of real world advantage.
You spoke about the hardware and the need to have deeper circuits. Um, would more qubits help? I mean, if you had a choice between a computer that
Mm.
can run a 10 times deeper circuit or has 10 times more qubits,
Mm.
would one be much better for
Yeah, yeah.
Monte Carlo than the other?
Uh, it depends on the application. I think on the Monte Carlo side, it's the quality of the qubits which is more important than how many qubits. We do need more qubits than we have today, but I think the bottleneck is really that we need to do these deep computations. So we need more depth. Of course, you can get more depth by error correcting your physical qubits. So if I had many physical qubits, I can use some of them to make fewer better qubits, let's say, right? But yeah, we need a couple of orders of magnitudes better fidelity than we have today. It is in the roadmaps of the hardware providers for the next 5 years, right? So we are not expecting something out of the ordinary to happen, right? And we are continuing to reduce, as you said, how many qubits do we need or how good these qubits should be and still get a good result.
Yeah, if I may add a little bit to Iordanis' answer, I think it also depends on the particular problem in finance we're talking about, because if Iordanis mentioned already that one of the uses of quantum Monte Carlo would be in option pricing, and there you have typically you have a few sources of uncertainty in the problem. So we'll have the price of the stock, maybe the volatility. You can also assume that follows some kind of stochastic process. You can add jumps to the process as well. So you might have a third source of uncertainty, or the stochasticity, and basically for each of these sources of uncertainty, you would need more qubits to deal with, right? So now if you move into a basket of options, where you have, 10, 15 assets, then the problem multiplies by 15. And if you move into the realm of, for example, credit portfolio, where Monte Carlos now deal with potentially millions of assets, then at the minimum you would need, even if you assume that it's only one source of uncertainty per asset, you would need at least 1 million qubits just to deal with the uncertainty from the assets.
Mm.
So it really depends on which application we're thinking of. That we can get away with just having fewer, better quality qubits than the more complex applications in finance that would actually need millions of good quality qubits.
Now, I think that the original Monte Carlo was invented in Los Alamos as part of the Manhattan Project, and obviously there were a lot of physicists and mathematicians there. When you guys work on these algorithms, even with that 5 year horizon, what kind of people do you need on your team to improve Monte Carlo? Are they more finance people? Are they biologists, quantum scientists? Is there a particular type of person that you're looking for to add to your team?
Oh, if I start, well, typically we're looking for people with technical education. So we're looking with people with masters or PhDs in a quantitative subject, and it can actually vary from people from a math, engineering, physics, economics, but also you can also go to the more specialist financial mathematics type of experts. But it comes to the advantage of having someone with more financial mathematics type of thing is that they know already the type of problems that we're solving in finance. But at the end of the day, these quantitative skills um, are they are very easy to transfer from one domain to another. So if you have good mathematical skills, good analytical skills, combined with a decent amount of IT programming skills, then you're in a good place, right? If you tick these boxes, it doesn't matter so much if you're coming from physics, mathematics, financial mathematics. You will, you will get there. Although I would say that in the beginning, it's always a steep learning curve to actually get to the level of knowledge about the financial industry that you would need to really be able to use those mathematical analytical skills to solve real world problems in finance.
Yeah, on our side, I think one important thing is the experience in building and developing new quantum algorithms. And this is something which is quite rare because we are not a very big community, unfortunately. So we need people who are very confident with classical algorithms and quantum information so they can start developing new quantum algorithms. But I agree with Gustavo that the the most impactful research happens when the expertise on the quantum side comes together with expertise from the finance side, because we do need to understand what is really the bottleneck and what do we need to care about or care less about, and what is really the problem that we are trying to solve. So understanding the financial part of this is really what the difference between a theoretical publication on quantum algorithms and a real financial solution with a quantum computer, right? So I think we need both. Yeah.
In the Yorgos, do you have something to add?
Yeah, I totally agree with both Iordanis and Gustavo. I would just like to add a small, comment that, in my experience, I found particularly useful. Um, I found particularly useful the interaction with people who understand stochastic mathematics, so stochastic differential equations, stochastic optimal control, and real analysis. And the reason is that often when we're at the initial stage of quantum algorithm development, sometimes we omit certain technical stuff about the speed ups we give and such. However, it is the case that you have to take into account small technicalities. For example, what type of function, what type of distribution are you working with? Uh, there's a difference between Holder continuity and Lipschitz continuity, and this affects it affects a lot. The bounds you give on your algorithms. There's no single answer, right? So I believe that a lot of disciplines can contribute. at different levels in the algorithm development, but they all have a difficult learning curve.
Very good. So, as we get close to the end of our conversation, I want to ask you one of my favorite questions. If you could have dinner with one of the quantum greats, dead or alive, don't say both dead and alive, no superposition here. Who would that person be? Maybe Iordanis, you're first, and then Gustavo, and then Yorgos, please.
Sure. Uh, so I think I had dinner with many of the people who are alive, so I'm very happy with that, and I'm sure I'll get some opportunity to eat with the rest of them. So I would go for someone who is dead for a long time, and I would say Niels Bohr. And the main reason is because Bohr actually had the right idea and the right intuition about quantum mechanics. And there was a big fight between him and Heisenberg on what does it really mean, what quantum mechanics really mean. And even though we talk more about Heisenberg and Heisenberg's uncertainty principles, it's actually Bohr's idea, which is the one that we believe today. So I would really want to have dinner with Niels Bohr and understand how he came up with all these counterintuitive ideas that actually are the ones that we believe today.
Okay, I think I would want to have dinner with Paul Dirac, and the reason is that I have to say you have to. I admire the passion that he had and the self belief that he had, that he had found the right solution when solving his for his famous equation that in essence predicted the antimatter, right, and the positron was found shortly, well, or I think it was a couple of years after he actually published his findings. But the fact that the entire community was thinking that it cannot be right because his solutions predicted negative energy, and that didn't make any sense. And he found the solutions that he had found so elegant that it had to be correct, and it was just a matter of finding the right interpretation. I think that was incredible, and I would love to hear from his own mouth how he actually coped with potential lot of pressure around him to basically ditch move away from that theory, um, and he managed to keep and to his guns and really basically dig up and dig and dig until he found a more plausible explanation, and it turned out to be the right one, and a massive new discovery for science.
Okay, so I would go with Alan Turing because I think he's a giant, and he's one of the people responsible for the age of information we live right now, including the quantum information and the ideas he sparked from philosophy to pure math to applied math to engineering. And his contributions are enormous. The notion of computable functions, what is computable and what is not computable. And yeah, I would be very curious to ask him a lot of questions and get intuition and inspiration out of him. I think that would be my choice. Maybe I would like to invite John von Neumann as well, if I were allowed. Yeah.
Excellent. And Gustavo, I had a previous guest that said that Dirac was not a very good conversationalist. He spoke very little, but when he spoke, it had a tremendous meaning. So I think my previous guest said, yeah, I'd love to have Dirac, but maybe we also have Feynman or someone just to keep everyone engaged.
Yeah, apparently, once Paul said to Feynman was, "Do you have a equation named after yourself?" That Feynman didn't. So like, that was it. That was the extent of the conversation. So yeah, I think it could be quite awkward that dinner with Paul Dirac. You're absolutely right, but still, it's one of my absolute idols. So I would love to spend the time, even if it was a very one-way conversation in the end.
Perfect. So, gentlemen, thank you so much for joining me today. What's the best
Thank
way
you.
for people to get in touch with you to learn more about your work? Maybe Gustavo, and then Iordanis, and then Yorgos.
Yeah, I mean, anyone that is interested in quantum computing and how we are thinking about utilizing quantum computing at Moody's can get in contact with me, and I can leave my contact details with you. And if anyone wants to reach out, can do. I'm also on LinkedIn, so anyone that is interested in knowing more about what we do can send me a contact request, and I'll be happy to accept, and we can have a conversation.
Yeah, the same through LinkedIn or through the QCWare website. We are collaborating with many people in finance, so we are always happy to talk more about these topics and yeah, work together to make it happen.
So for me, it's the same. You can find me on LinkedIn. And yeah, if you want to know anything about how we use quantum in HSBC and what we're interested in, what we're doing, I'll be happy to provide answers and engage into nice discussions, and also, of course, through archive papers and such. So um, there are ways. Yeah, absolutely.
Excellent. Well, thank you so much for joining me today.
Thank you.
Thank you.